Good morning, everybody, and thank you for attending today's webinar. My name is Matthew Byer. I'm part of the technical sales team at ThermTest, and today we will be discussing the thermal conductivity and thermal resistance of rigid and compressible insulation. I will now be handing it off to my colleague Dale, who will be conducting the presentation.
Hello, thank you for joining. We'll talk a little bit about measurement of thermal conductivity and resistance on rigid and compressible materials. So hopefully this will be an interesting talk, but thanks for everybody for joining. So the agenda, some of the things we'll discuss briefly is what is thermal resistance and conductivity. I like to start with these definitions because it sets up for what we talk about in the following slides. What is effective or apparent conductivity? That is a set of words that you see quite a bit. What does that really mean? Who cares about thermal conductivity? How does that relate to thermal simulations? We'll compare two common thermal conductivity methods. Certainly not all the methods that are available to measure insulation. Just wanted to talk about two very common methods that you'll see in specifications and publications, and some glossary of terms. So what is thermal resistance and what is thermal conductivity? Resistance is the ratio of temperature difference across two faces of a material or across the thickness. The higher the resistance, the lower the heat transfer, and the reverse is true. The lower the resistance, the higher the heat transfer. So what makes resistance valuable is it's the most appropriate measurement for characterizing non-homogeneous materials where other modes of heat transfer are present in addition to conduction. So that would be low density materials, the nature of it being a non-solid or semi-solid. Thermal conductivity refers to the intrinsic ability of a material to transfer or conduct heat. It is intrinsic to the material. This is the most appropriate way of characterizing homogeneous materials, or what we like to describe as micro-homogeneous materials, so it creates more clarification on what we mean by homogeneous, where the only mode of heat transfer is conduction. So it's intrinsic, it's a physical property of the material, and it's independent of dimensions of the sample. So typically what we talk about when we talk about dimensions is thickness. Effective or apparent thermal conductivity. Again, this is, I wanted to add this slide to discuss something I see quite a bit. It is the thermal conductivity has been measured to as close to possible as the true value. There's been a source of error that have affected the accuracy, and those sources of error have been identified. What I'd like to see, and hopefully we can create more education on this matter, is when effective or apparent thermal conductivity is listed as the measurement, there should be a note or comment in the reports or specifications on what that source of error that makes it ineffective or apparent. Because if it's a solid where conduction is your only means of heat transfer, and you're using a valid method, you can just call it thermal conductivity. Examples of the sources of error that might show up in apparent or effective classification are convection, radiation, porosity, fillers, micro heterogeneity, macro heterogeneity for sure, and contact resistance. So one good example of the effects of contact resistance is in electronics when they use a guarded heat flow meter, which is ASTM 5470, for measuring the thermal conductivity or the effect of thermal conductivity across the thermal interface material. It includes, and that's a valid, desirable measurement, includes the contact resistance, because in that application, that has an impact on the performance of that thermal interface material. So it's important that definition is included. So who cares about thermal conductivity? This is a very broad slide that talks about some areas of industry and academia that are interested in this property. So it's used in general R&D, quality control, optimization, which means selection of materials for use in an application, specifications, so that would be a company that makes something, let's say, and they want to measure thermal conductivity to put on their specifications. And there are several industries and material types where thermal conductivity is a very desirable property that they want to maximize. So it's really important to be critical of specification sheets and look at the means and method and way they made these measurements. Ultimately, where does all this data end up? Who ultimately cares about the accuracy and the true nature of those measurements? Well, a large amount of that data is used rather in thermal simulations. So what do I mean by thermal simulations? I know everybody knows, but just a quick overview. Thermal simulations are generally done in steady state, one-dimensional analysis, which is of a constant thermal load on a model to determine temperature, heat flows, heat fluxes. Once those are achieved, or alternate or additional transient analysis can be performed to determine initial conditions, a power on condition, a temperature on condition, etc., where transient can act different than steady state. But the key is often these simulations are done with steady state one-dimensional properties. Measurement errors that can be transferred to simulation, so that's in the lab data or on a specification sheet that can make its way to a simulation and cause errors in the simulation, are that the measured thermal conductivity is represented as one-dimensional, but it is not one-dimensional. That could be a bulk measurement on an anisotropic sample or an average value on an anisotropic sample. That is not one-dimensional. You'll have a skewed result because of that, which will cause error when you assume it's one-dimensional. Non-steady state. So if you're doing a steady state simulation and you use transient data, so measurement by a transient method, and there's some error in that transient measure that's causing the results to be not representative of the material, of course, that will affect the simulation because it's assuming that data is steady state. Some examples of that, which we'll talk about in some slides, are thermal shunting, convection, poor fitting of the calculation model to the material you're using. So we'll talk a little bit about those. So the two methods we're going to talk about generally for measurement of insulation, and these two methods are used widely for insulation because they both have strengths, one of them being with the transient method, one of the strengths being small sample size. Of course, in an R&D lab, the ability to measure small samples is highly desirable. So what gives it the ability to measure small scale is the typical scale times are 1 to 80 seconds. So again, small time means that you're keeping your heat within the boundaries of a semi-infinite body, which allows you to test small samples. Typically in the millimeter scale to 75 millimeters. That is now you can say it has it's unlimited for sample size, but there's certainly a limit on how far your data, or rather heat from your sensor, which is your testing signal, can penetrate. So it's the best way to describe that is there is a sample size limit based on the instrument's ability to penetrate. Those models, meaning the math that's used to calculate the conductivity from the raw data, assumes 100% of the heat introduced from the sensor to the sample diffuses through conduction. Any other mode of heat transfer or any other thermal leakage causes error in the model. The amount of error is determined by the amount of that leakage. Can there be corrections to these if you know specifically what that leakage is, if you know specifically what that effect is that's causing a misrepresentation of heat of diffusion? You might be able to correct for that, but that's quite complex. So the other variable that plays an important part on accuracy of transient is that there is a shape based off the sample configuration or the shape of the sensor, which determines what you're measuring. So it's really important to understand the material you're going to measure, whether or not the sensor and calculation model are valid for it. So one of the most common calculation models for a disk or a plane source is three-dimensional. Well, when you introduce that that sensor to a sample, the math assumes, and it makes assumption that the heat is diffusing in all directions the same. So isotropic. Why I describe it as also microhomogeneous is that any degree of heterogeneity and an increasing amount of heterogeneity will cause distortion in that shape of three-dimensional penetration and cause errors in your calculation model. The smaller those are, the less effect. So there's really a wide range of potential error. And knowing your material on that scale is an important way of understanding how you describe that effective value you're measuring. One-dimensional, basically you can fit a more conductive type material, not an insulation type material, but a more conductive type material. You can fit the dimension or the diameter of that material to the sensor, and it provides some passive guarding and a one-dimensional heat flow. that particular testing approach requires the input of density and specific heat. The last way, which is a calculation model, again, there's no guarding in the anisotropic testing capability. So it's as the heat naturally diffuses into the sample, the model, the calculation model for that approach assumes that the fibers, the particles, or whatever is causing the anisotropy is highly organized in repeating through the thickness. Thermal conductivity, if it's not repeating through the thickness, you'll have some sensitivity to that. That's a difficult way to classify a material that has a thickness, that you have ever-changing through thickness thermal conductivity based on the model you're using. So we have a few examples of that. So the two methods, the additional method rather that we're going to use is a heat flow meter. This method's been around for quite a long time. The test times are typical to the type of material you're testing. They have the thicker the material is, the more insulated it is, the longer it takes for steady state to achieve. So you have a hot sample, rather hot plate, and a cold plate with a delta T across your sample of, let's say, 20 degrees. There's a flux sensor integrated into each plate, upper plate, bottom plate, and we're looking for the composite flux of those two plates to become steady state. What's the advantage of that? That advantage is that is actually measuring a large sample. That's key. That is not a drawback. It's designed to do that. So that enables it to measure heterogeneous materials, not only homogeneous materials. It is a passively guarded system. So the distance from the flux sensor in the plate to the edge of the sample provides passive guarding such that the heat penetrating from one plate to the other is one-dimensional. So the measurement of resistance, if you have effects of conduction, convection, or radiation, you're going to see that in your measured resistance value. And resistance is the proper way to measure that. The time it takes for steady state to be achieved, these types of additional modes of heat transfer or heterogeneity, which will negatively affect a transient, which the steady state is not the condition. Those types of errors are mature and have been stabilized through the steady state approach. So you basically have a stable conductivity despite these material properties or material characteristics that can affect other measurement approaches. So what we did to demonstrate some of this is we took a construction expanded polystyrene. I call it construction because it is not homogeneous. So it is heterogeneous on a scale that will cause distortion in the heat of diffusion. So what we took is we took 3 diameters of a transient sensor, or 4 rather, and introduced them at max time scales to maximize the amount of volume we are penetrating in the material, because that's the best rule of thumb. I did the small ones. We did the small measurements of diameters just to demonstrate this effect, how you can see that if you're measuring on a very small sample scale, your data can be very skewed. So here you can see with the increase of diameter, an increase of time, we have an increasing penetration depth, or the amount of that sample represented in the data. So you can see a stabilization of the data from the heterogeneous nature of the sample. Now, if we did this exact same experiment with glass, these thermal conductivities would all be the same. So that's an important difference. So heterogeneous, why do we use thermal resistance for the measurement of heterogeneous, is for this type of approach. So how does this compare to a steady state approach? Let's compare the numbers. So we took that same sample of 50 millimeters thickness and introduced it to a heat flow meter. Those 2 plates come together and there's a delta T across it. So this was tested at a mean temperature of 20 degrees. One plate was 30 and the other plate was 10 degrees. And we took that same sample, flipped it over, and you can see the thermal conductivity is quite a bit higher. So there's a bias between the resistance-based thermal conductivity. This is a side-to-side, or the full thickness is represented in this resistance. So you have a true value of thermal conductivity where any errors that affect the transient are stabilized through the steady state condition that we achieve. typical test times are 20, 30 minutes based off the thickness of the sample. So an important detail to point out is this is a calibrated method. It's a comparative method. So NIST offers a variety of materials, and the standards refer to that the reference material you're going to use should be of a similar density and nature, such that the contact resistance is being minimized through that calibration approach. And that was done for this data. So what are the conclusions or observations, I should say, between the transient comparison and insulation? And there are a number of papers that discuss transient measurements on insulation and compared to steady state. And some of this explains those differences. There are very unique cases to various materials that explain it uniquely, but generally these should help a bit. Measurements show sensitivity to heterogeneity. Large sensor and long time scales are still not representative. They have a more or less three-dimensional shape, but they do not represent a one-dimensional measurement, and they don't represent the full sample in its thickness. So those types of things can cause error in your simulations or when you're comparing to steady state methods. Three-dimensional shape, there is a distortion. There has to be, because it is not homogeneous. What is the degree of that distortion and its effect on the calculated conductivity is specific to the material testing. The greater the difference between the particle or phenomenon that's causing the degree of heterogeneity and the matrix, the greater the distortion of that shape. Again, it expects that heat is penetrating in all directions the same, so three-dimensional. So when it's not three-dimensional, there's an error in there. The amount of error is really specific to that material. Steady state, there's a large sample that is used as the measurement, and that's on purpose by design. In this case, it was 1 foot by 1 foot by 2 inches thick. There is the sensitivity to the transient effects are stabilized at the steady state condition. Again, often that data is used in a simulation where steady state is the desirable use of that data. So there's poor correlation between the methods in this case because the materials are heterogeneous. If those samples are micro-homogeneous or very homogeneous, the correlation between these methods can be quite good. So again, I use the example of glass. If you measure glass by these two methods, you get very good correlation. So another example of this approach, or looking at insulative type materials, is the NIST 1450D. So what we did is we took, I should specify, this material is quite anisotropic. It has aligned fibers in the in-plane direction. So the three-dimensional calculation model does not apply. You cannot use the three-dimensional calculation model. It's true it will give you an average number. It'll give you an average number weighted somewhere between the in-plane value and the through thickness value. Is that weighted average value accurate? It's hard to say, and it's hard to verify that. So the NIST expected value that is reported for this is 0.0323 watts per meter Kelvin. We took 3 sensors. Again, we use max time scale for the anisotropic module and each specific sensor to maximize the penetration depth for each sensor for both axial and radial directions. And you can see here that we did these are diameters 6.4, 12.8, and 60 millimeters. And there's a corresponding longer length of time with each one of them to maximize the time scale for each. This is an average. I put that in there because you can see the effect of average. It does stabilize with the larger sensors, but what does that number really represent? It's somewhere between the two directions, and it's a weighted number. What is the use of that? There are applications, but specific to looking for a one-dimensional value, it's a consideration. So here you can see the axial value and the radial value and the corresponding penetrations for each. What's really interesting is that the 80 seconds time scale of a 12.8 millimeter diameter sensor, the axial direction is not too bad. The correlation's okay. But there's a very specific requirement for using the anisotropic module, and it's such that the thickness, the anisotropy through the thickness is repeating and highly organized. Meaning, if this material's anisotropy was repeating and highly organized, you could penetrate at different thicknesses and you would have the exact same axial thermal conductivity. So in this case, it's a unique use of that one time in that one sensor that averages that particular amount of material in each direction for that number. But if you underpenetrate it or rather penetrate less than that or penetrate more than that, your actual value changes. And that's because it is not repeating. So it's really important that when you use an anisotropic approach with a transient this type sensor, that your material is highly organized and repeating to get valid results. Otherwise, what are you measuring? You will have error associated with that. So we took those same materials and measured them with a steady state, a heat flow meter. Sample size is 300 millimeters by 300 millimeters by 25 millimeters thick. Again, the NIST material, I just put this as a reference to compare for the data below. The reported NIST value is through thickness at 0.0323 at 20 degrees Celsius. The sample fully is inserted between the two plates. And then we took, from a suggestion from a colleague, we were kind of curious of how we would approach an in-plane value. Now, this is an estimation approach only because there are an effect of the putting materials like this together. There will be a parallel effect of that, but it's an interesting estimation of that in-plane value. We cut 1-inch slivers and turned them 90 degrees and sandwiched them, and put them back in. You can see that there is a very real effect of anisotropy. The axial value or the through thickness value correlates quite well with the reported value, and that's an interesting phenomenon that you have the ability to measure anisotropy or an estimation of it. Again, the estimation of that property is somewhat comparable to the 80-second measurement using the anisotropic testing module or calculation module for the specific sensor and diameter. But it's a specific penetration in time that gives you that average value, and it's not repeating. So you don't have that. If you were to measure all the way through the thickness, as I'm approaching here with 24 millimeters, you can see that value changes. So what's the observations when comparing those two methods across that sample? Measurements with transient show sensitivity to sample heterogeneity and non-repeating anisotropy. Those are requirements of use of transient. So it's not a surprise that some of these phenomena would cause some differences in bias between the two methods. The large sensor size and long time scales improve representative data or volume, but in this case, it's not fully. It is not the full material through thickness and guarded. Anisotropy is not highly organized, as I mentioned. Thus, the anisotropic calculation model has some degree of error. That 80-second measurement axial value has good correlation, but again, as it's non-repeating, your axial value changes with penetration depth. If that material is repeating, you would have more or less stable thermal conductivity in those calculations. Steady state, in this case, because of the nature of that sample, it is an advantage to test at a larger sample size. So that's the thickness, you're measuring resistance across that full thickness. This, again, the sensitivity to transient effects are stabilized due to the steady state conditions that's met. And that passive guarding that's caused by the sample being bigger by a certain factor than the flex sensor provides passive guarding. So in this case, there's poor correlation because of the disorganized anisotropy of that material. So again, it's really important to use the proper method and or calculation model, knowing your material. And if there was a material, there's not many, if there was a material on this scale of size that was highly repeating and anisotropic, you would find good correlation between the through thickness value from a heat flow meter and the through thickness or axial value from a transient anisotropic calculation model. You would find good correlation. So what are some final thoughts? Thermal conductivity is not simple. There are some 20 ASTM methods. There are many more than that that are specific built for different applications. There is no one method fits all. There are application of single methods. That doesn't necessarily make them the most true. So for true measurements of thermal conductivity, care should be taken to select a method that is designed for your sample. So you really have to know your sample. Is it isotropic? Is it homogeneous? That opens up doors. Look at your sample configuration in terms of size and dimension. If it is not isotropic or homogeneous, consider if it's insulation or conductive. There are ways to approach those materials. So transient, your material should be micro-homogeneous. If you're using a three-dimensional calculation, it should be isotropic. Some small degree of anisotropy will cause small error. Large degree, that's non-repeating, will cause larger error. Anisotropic calculation that's highly organized and repeating is a good candidate for measurement by this technique. Steady state, it's more robust for measuring, of course, it can measure homogeneous, but it's more robust for measuring heterogeneous materials, micro to macro types. True measurement of conduction and other modes of heat transfer, low density materials. That's why this is the go-to method for looking at insulative materials over a large thermal conductivity, large thermal conductivity range, which are very porous. And of course, those are going to have other modes of heat transfer. So this is the go-to method for those types of materials. Some glossary terms, really the one that I probably would point out is the use of effective. Basically, it's a description of that we've measured the best we can to get as close to possible of the true value of that material. There are sources of error. Those have been identified. Those should be described in some way so that the reviewer or user of that data has an idea on how that may affect his use of the thermal conductivity. There's some upcoming webinars. This would be for the coming months. Please feel free to look at these on our website. You can, there's some very interesting areas we're looking at. So I think now we're going to have a Q&A. So if anybody has any questions, please type them into the message box. We'll wait a few minutes. Usually there's, it does take some time to put those into the message box, so we can wait a few moments. So maybe there's no questions. If you have any questions offline, feel free to toss us an email. We certainly will reply to those with whatever any questions you may have. Thank you for joining us, and have a great day.